Hey folks, we're looking at class 46. This is an introduction to gravity, specifically Newton's law of universal gravitation or the universal law of gravitation. So what we're doing is we're not quantifying the force of gravity in this class. We're just trying to understand how does the force of gravity change when we change the mass of either object, and how does the force of gravity change when we change the distance between those objects. So there's a simulation here. Get that open if you didn't do it in class. Basically, what we found using this simulation was that as the distance between objects gets bigger, the force of gravity gets smaller between them. As the distance gets smaller, the force of gravity gets bigger. This should make sense to you because you feel the Earth's gravity every day because it's really close to you. You don't feel the force of gravity from Jupiter because it's really far. What do you notice about the magnitude and direction of the force of gravity acting on mass 1 as compared to the force of gravity acting on mass 2? Never forget, all forces come in pairs, equal in magnitude and opposite in direction. So, and they act on different objects. So, if object 1 feels a force of gravity from object 2, object 2 feels the exact same force of gravity from object 1. So they're equal in magnitude but opposite in directions. Now, those forces will always change depending on how we move the objects, but they're always equal to each other. At any given point, they're equal to each other, pointing in opposite directions. So check out the simulation, if you haven't already. So we took some data from the simulation. What we did was we set each mass, I think one of them was 4 kilograms and the other one, or 4 billion kilograms, and the other one was 2 billion kilograms. We set them 2 meters apart and we started taking data for the force of gravity between the objects. Here is the data we took. Notice how when the distance between their centers, because that's what R is, the distance from center to center, when the distance increased, the force of gravity decreased. We graphed this. We got this nice, this is an inverse relationship here. This is not a straight line. Purposely, this is not a straight line. So this makes sense because as distance gets bigger, the force gets smaller and vice versa. Right, and that's what we kind of state in 7 and 8. Now, why is this an inverse relationship? Because one goes up, the other goes down, and vice versa. So how would the force of gravity change if you double the distance between the objects? Well, we know it's going to go down, but how does it change? Now, a lot of people, their knee-jerk reaction is, oh, double the distance, you must cut the force in half. Well, let's check out our data. So when we double the distance, that would be like going from 2 to 4. Our force went from 133.5 to 33.4. Well, how much did that go down by? That's hopefully you notice that's not half. It didn't get halved. Let's see. So 33.4 over 133.5 is almost exactly 0.25 or 1/4. So when we doubled the distance, we actually got 1/4 the force of gravity. Well, what about when you triple it? Well, when you triple it, that would be like going from 2 kilometers to 6. Is it cut in 1/3, 1/6? What is it? Well, it went from 133.5 to 14.8. Let's check it out. 14.8 over 133.5 is 0.11, which is 1/9. So when you triple the distance, you get 1/9 the force of gravity. So this is no ordinary inverse relationship. This is an inverse square relationship. Okay, so whatever change you make to the distance, you square it. And that is the effect it has on the force of gravity. So Newton was able to conclude that the force of gravity is proportional to 1 over r squared. Now, r is not the radius of a planet. It is the distance from the center of one object to the center of the other. Why do we use r? I'm not entirely sure, but my guess would be that when Newton or whoever was first doing calculations like this, the distance between planets, or the distance, let's say, between the Earth and the Sun, is equal to the radius of the Earth's orbit. So I think that might be why. I'm not 100% sure. Don't quote me on that, but that would be my guess. So r is the distance from center to center, not half of that distance. Now, how about masses? Well, play with the simulation, change the masses without changing the distance now. Hopefully you notice that as the mass got bigger, the force got bigger, and as the mass gets smaller, the force gets smaller. Again, this should make sense to you. The Earth is pretty close to you. It's got a really big mass, so you feel the force of gravity from the Earth. Someone sitting right next to you has much, much, much less mass than the Earth, and you don't really feel the force of gravity from them. So obviously, more mass, more gravity, less mass, less gravity. So we set up the objects each 4 kilometers apart, each with a mass of 1 billion kilograms. All right, don't change the distance for this activity, and we just took some data, finding what the force of gravity was in each case, and we have the products of the masses there. So as mass increases, force of gravity increases, and vice versa. So we call this, a lot of people say a direct relationship because as one goes up, the other one goes up as well. Well, how does it go up? Well, let's see. So how does force of gravity change if you double one mass? So an example of that would be like going from this first row to the second row. You're just doubling one of the masses. So when you double one of the masses, hopefully you see this, the force doubles as well. Now that's a little bit rounded, that's why it's not perfect, but the force doubles as well. Well, what if you double both masses? Well, that would be an example like if I go from this first row here to this row here. We went from 1 to 2 and from 1 to 2. Well, let's see, 16.7 compared to 4.2, it quadrupled. Okay, so when we double each mass, the force of gravity quadruples. So this isn't just a direct relationship, this is a linear relationship. And Newton was able to conclude that the force of gravity is proportional to mass 1 times mass 2. Okay, not just mass 1 or mass 2, mass 1 times mass 2. That's why we have this column where we have the products of the masses. Okay. In this case here, when we doubled each of them, the products of the masses went from 1 to 4. So the force of gravity got quadrupled. So Newton was able to put those two ideas together and write that the force of gravity is equal to big G m1 times m2 divided by the distance between them squared. Specifically, the distance between their centers. Big G was a constant. Newton really couldn't quantify the force of gravity, so he knew there was some constant there that would bring it into newtons. He just couldn't really calculate it. It wasn't until someone called Henry Cavendish came by years later, he was able to figure it out. So a couple of big takeaways. As mass gets bigger, force of gravity gets bigger. As mass gets smaller, force of gravity gets smaller. That's a linear relationship. And as the distance gets bigger, force of gravity gets smaller. And as the distance gets smaller, the force of gravity gets bigger. That's an inverse square relationship. So here's a question kind of tying the two ideas we spoke about today together, and we look at it more next class. So how does the force of gravity change if you double the distance between two objects and double the mass of one of them? Well, if you double the distance, we said you quarter or have 1/4 the force of gravity. And if you double one of the masses, you double the force of gravity. So how do we put those two together? Well, it's really the only way that makes sense to do it is to say 1/4 times 2. You multiply those two changes together, and you get 2/4 or 1/2 times the force of gravity. So if I double the distance between two objects and double the mass of one of them, I have 1/2 of my original force of gravity. Now the force of gravity is not equal to 1/2, it's simply half as strong as it was before I made any changes. All right, folks. So have a good day. We'll check out this exit ticket question at the beginning of next class. See you next time.